And let's go ahead and summarize 5.1 because this is probably a new concept to you, and I want to give you a kind of an overall summary of what we've talked about so far. Let's go ahead and scroll back up to the top. All the way back up. This whole section was trying to describe what the electrons are doing inside the atom. And so in order to understand what the electrons are doing, we have to use light. We cannot look inside the atom. It's too, well, number one, it's too small, and as we learned in the chapter, even if you were able to look inside of it, the electrons would be bouncing everywhere anyway, so you wouldn't really be able to get a good look at it. But anyway, light exists as and behaves as a wave. It's got a wavelength associated with it. The longer the wave, the lower the frequency and the lower the energy. Depending on the wavelength, it will behave in certain, or we will describe it in different ways, such as radars, microwaves, UV light, gamma rays, or visible light. The longer the waves, the lower the energy. The shorter the waves, the higher the energy. What you only need to know from this particular section is that you need to know Roy G. Biv, and you need to know that red light is low energy, violet light is high energy, and it follows a whole continuum. You do not have to memorize the wavelengths that would be considered radio waves or microwaves or X-rays or whatever. Just know Roy G. Biv. The red side is the low in energy, the violet side is the higher energy. Alright, scrolling down. Albert Einstein described light as particles. Alright, the fact that he could describe light as particles gave rise to what's called the photoelectric effect, where when photons of light strike a solar panel, they can generate electricity. This is incompatible with the wave nature of light. The fact that light behaves as a wave would not give rise to solar power, but the fact that it can behave as a particle does. Now on the flip side, the fact that light behaves as particles would not give rise to things like rainbows and those types of things, and there are other properties that are not compatible with the particle nature of light. This paradox is known as the dual nature of light, because light does behave in both ways, but we don't know exactly how it can behave both at the same time. It is definitely not a particle moving in a wave pattern through space. They are just two separate models that happen to work at different times. All right. Now, understanding that as far as light, now we can start using light to help unpack what these electrons are doing, and Niels Bohr was one of the first guys to do this. What he did is he was looking at how the electrons were absorbing and emitting energy. Now, the closer to the nucleus an electron is, the lower in energy it is. The further away from the nucleus it is, the higher in energy it is. And what he was looking at was saying, as electrons absorb energy, they move away from the nucleus, but where exactly can they move to? What they were expecting was that the electron could move at any distance from the nucleus and could absorb and then emit any amount of energy. And if it could do that, it would give off all wavelengths of light. You would see a full spectrum, because as the electron absorbed and emitted energy trillions upon trillions upon trillions upon trillions of times per second, you eventually would see all the various possibilities of the electron at different distances, and you would see all the possibilities of energy or all the colors of light being emitted. However, that's not the case. Hydrogen, for example, only gives off 5 lines in the visible spectrum: a red, a teal, a blue, and a couple of violets. And what that suggests is that the electron cannot absorb and emit any amount of energy. It can only absorb and emit fixed quantities or discrete packets of energy, and can only exist at discrete distances from the nucleus. It cannot travel where it wants to. If we look at this particular diagram here over on the right, what we're seeing is that the electron in its ground state, meaning where it is normally, it can absorb a certain amount of energy. And I'm going to change my color here to blue just to highlight this. It can absorb either this amount of energy, and so on and so forth, but it cannot absorb anything in between those. As it absorbs that energy, it becomes excited, and when it returns to a lower energy level, it gives off a certain quantity of energy as it returns. Now, this happens in the blink of an eye. All right. What Niels Bohr said was that would correspond to electrons traveling around the nucleus like planets around the sun. They travel around in fixed pathways called orbits, and those orbits are associated with a certain amount of energy. Of course, the closer to the nucleus it is, the lower in energy it is. All right. Now, if an electron was in the lower energy level, I'm going to change to, because I already got blue on there, I'm going to go to, let's say, green here, just to switch this up. If an electron was at a lower energy level, say at n equals 2, the second energy level, all right, and it's sitting right there, it can absorb either this amount of energy, or this amount of energy, or this amount of energy, but nothing in between that. If it absorbs that full length, this amount of energy, and becomes excited, and I'm going to put that in quotation marks, it can then return either to this orbit, or this orbit, or it can go all the way down to n equals 1. But it can't stop anywhere in between. Wherever it jumps to, in an instant, it does not gradually fall, it goes in the blink of an eye. It's got to give off whatever quantity of energy is different between the two orbits, and it gives it off as a photon of light. And so there are only certain jumps that can possibly happen, and those certain jumps are what correspond to the certain lines that are given off in the line spectrum. All right? So this model was very promising because he was able to calculate perfectly what lines are given off by which jumps. And again, that could be a source of extra credit for those who want to do those types of calculations. They're actually not, it's just simple algebra. Now, that model was looking pretty good, except it only worked for hydrogen. It didn't work for anything else. So though the scientists tried, they could not describe the electron moving as a particle. So they had to change. They had to change their model to a wave model, where electrons are described as a standing wave, like a guitar string. Now, that also provides a problem, or presents a problem, in the fact that when you do the calculations on that wave, you cannot know both the position and the momentum of the electron at the same time. That's Heisenberg's uncertainty principle. So instead of describing the electron as in a fixed position or a perfect position, we have to describe them as probabilities. That's what we do in what's called the wave mechanical model, or the quantum mechanical model, or some people call it the electron cloud model. All three of those names are talking about the same model. All right. We can describe the allowed energies, or the allowed distances from the nucleus that the electron can have, and we can say the likelihood of finding the electron, but we cannot know exactly where it is. We're dealing with probability areas and probability distances from the nucleus. Okay? When you start looking at the probability, we simply designate 90% of the probability as an orbital. An orbital is not an orbit. An orbit is a fixed pathway. An orbital is a probability area that we describe 90% of the probability of finding the electron. These probability areas have different shapes depending on the type of, or depending on the electron you're talking about. Some of the probability areas are spherical, and we call them s orbitals. Some of them are peanut-shaped, we call them p orbitals. Some of them are daisy-shaped, and we call them d orbitals. And there are also f orbitals, which have become more complex. Now, each distance from the nucleus, or each energy level, has orbitals in it. The first energy level only has the s orbital. It's spherical. The second energy level has both s and p orbitals. The s orbital in the second energy level is just like the 1s, except it's going to be bigger. So if the gold is the 1s, the blue here can be the 2s. And then it also has the p orbitals. When you get to the third energy level, which is further away from the nucleus, you're going to have s orbitals, you're going to have p orbitals, and you're going to also have d orbitals. The s orbital in the third energy level is just like the 1s and the 2s, except it's going to be bigger. The p orbitals in the third energy level are just like those in the second energy level, except they're going to be bigger. And then, of course, you have the d orbitals. When you get to the fourth energy level, you again have s orbitals, p orbitals, d orbitals, but you also have what are called f orbitals. The s orbital in the fourth energy level are just like the ones in the first, second, and third, except it's bigger. The p orbitals in the fourth energy level are just like the one in the second and the third, except they're bigger, and so on and so forth. The orbitals simply get bigger or further away from the nucleus as you go higher in energy. Okay? Now, in the next section, 5.2, we're going to talk about how we describe the electron and how we know which particular energy level and which particular orbital the electrons are put into. All right? We'll see you next time in 5.2.